Okay. So yesterday we started talking about trigonometric equations, and we started off with just some basic ones where we're isolating the trig function, but very quickly we're going to start to see that that's not going to be possible, so we have to start using different techniques to help us out. But I did ask that you went home and tried to solve 3 tangent squared of x minus 1. All right, so let me write this out. Okay, so in just a moment, I'm going to get somebody up here. All you need to do is solve it for tangent. Just tangent of x equals, find me that ratio, and then I'll take over from there. I'll go ahead and start looking at the triangles and finding the angle measures. Okay, but just a couple reminders. Today was the last day if you wanted to retake the test, and I had a lot of people come in, so if you were one of them, thank you very much. Tomorrow morning is the deadline for the Happy Minutes retakes, from the week of the 14th to the 18th. Okay, so if anybody is still in that category where you have some of those failing, please come in by tomorrow morning. Let's get that taken care of, take advantage of it. And as of right now, we still have the test next week. So the test will cover the double angle identities, okay, which you just went over. Okay, so in fact, question 1 on the test is going to be real similar to that quiz you just took. In fact, how was that quiz? Was it easy? Okay, we needed a win. Okay, good. And the rest of it's going to be the equations, solving equations. Okay, so double angle identities and equations. So with the 3-day weekend, you could take Monday, go ahead and start preparing for the test. It is not too early. Okay, but let's take a look. So who wants to come on up and solve 3 tangent squared of x minus 1 equals 0? All you have to do is rewrite it, tangent of x equals. Get everything to the other side. Okay, got another text message. Skylar, you're volunteering? Okay. I do have the random number generator pulled up in case I don't have one. Dylan, you want to do it? All right, Dylan will do it for me. All right. Okay, so I'll take care of the triangles. We just need to isolate tangent. Okay, so first we add the 1 over. Okay. Okay, then he divided through by 3. And to get tangent from tangent squared, I'll take the square root. Yes. Very close. So it'd be 1 over what? Okay, so he even went ahead and rationalized it. Very good. Thank you. Excellent. Now, does anybody want me to go back and revisit how he got that square root of 3 over 3? Everybody feels confident they could do that? Okay. Now, there is one thing he did forget, the plus minus. There we go. And that also answers the next question. Why do I have a triangle in each of the 4 quadrants? Well, where is tangent both positive and negative? It's got to be all 4. Okay. So we've got tangent of x equals plus or minus the square root of 3 over 3. And I think from here, if people can get to this point, you should be okay, especially using the triangles to figure out what your angle measures are. I think the most difficulty we're going to have is just getting to that point. What strategy is going to help me actually solve and get the ratio? Okay, so what ratio is tangent anyway? It's what over what? Y over x, right? Okay, so we're going to go ahead and say that y is the square root of 3. Okay, x is the 3. All right, and remember, we always do this from the reference angle's point of view. So like this first triangle here in quadrant 1, I'm going to go ahead and say this is the square root of 3 height with a base of 3. Okay. The triangle over here, square root of 3, 3, but it's going to be negative. And then we're going to have a negative square root of 3 right here, negative square root of 3 as appropriate to the quadrant that we're in. Is everybody okay with what I've done? Any questions? What would the hypotenuse be? Yes. You could, and actually I'm going to bring that up at the end. You could actually do that if you wanted to, yes. Okay. So what's the hypotenuse? Okay, so it'd be root 12, which is 2 root 3, 2 square root of 3. 2 square root of 3, 2 square root of 3, 2 square root of 3, and 2 square root of 3. Would anybody like me to go through the Pythagorean theorem to show how we got that? Okay. Now remember, everything we're going to be doing in the beginning, all the way through the test, what kind of triangle should you end up with? Special. It's got to be a special. 30, 60, 90, or a 45, 45, 90. The only way you're not going to be able to get a triangle is if you have a, starts with a Q, quadrantal. If it's a quadrantal, we're actually going to see several of those today. So what type is this? It's 30, 60, 90. It is definitely not a 45, 45 because the two legs are not identical. And if you take a look, it still fits the pattern. The hypotenuse is exactly double what the shorter leg is. And in order to find the longer leg, what do I do to the shorter leg? Oh, I square it. I take square root of 3 and I multiply it by square root of 3. You take the shorter leg and multiply it by square root of 3, and that would give you 3. Okay, so the only question left is this one right here. Is that 30 or 60? That is 30, because the square root of 3 is the shortest side, and that has to be across from 30. 3 has got to be the longer leg. So all of these reference angles are 30. Now remember, when we're looking for the angles that make this equation true, we start rotating from where? Where do we start rotating? What do we call that position? Standard position, the positive x-axis. So I want this one, I want that angle, I want this angle, and I want this angle. And just be careful if you're going to rotate all the way around, that additional angle is 60, okay, not 30, because the reference angle is 30. All right, well, we already have the first one. We know that's 30. Okay, so what's the second angle? How far would I rotate to get a reference angle of 30 remaining? 150. Then 180 plus 30. Okay, 210. And then the last answer, instead of maybe going all the way around, what's 360 minus 30? 330 degrees. Now, this is something that I did get into the habit of when I was solving these. And if you like it, great. If not, do your own thing. But especially when I draw the diagrams, I go ahead and write the measures as degrees. And then when I write my final answer, I just go ahead and convert it. Okay. If you feel confident enough to go ahead and convert it, please do so. We know by now 30 degrees is what? Okay. Pi over 6. 150. 5 pi over 6. 210, 7 pi over 6, and 330. 11 pi over 6. So those are my solutions on the interval 0 to 2 pi. Now, you want to be careful because the instructions, if it says find all solutions to the equation, well, then you're going to be writing your answer in the general form. You're going to be adding plus 2 pi n or pi n depending on the trig function. Okay, but it could also say find all solutions on this interval. So if you're given an interval, you're always going to be giving me specific answers. The only time you're going to give me the general is if you have no interval provided. Does that make sense? Okay. Now this is what Aiden was talking about a second ago. Let's say I did just want to find all solutions. It wasn't on an interval. So I'd go ahead and write these in the general form. So like, for example, pi over 6, what would I add to it? Now, it wouldn't be 2 pi n.
Oh, it's tangent. So
there you go. Remember, tangent and cotangent, they're the only ones with periods of pi, so it would just be pi n. Now, in fact, I would only have to do this one more time. 5 pi over 6 plus pi n. I would not have to go ahead and put 7 pi over 6 plus pi n or 11 pi over 6 plus pi n. Okay? Because if you go ahead and take a look, for example, if I have pi over 6 and I did actually add pi, well, what does that come out to?
7.
Yeah. So see, that general form would already take care of that 7 pi over 6. Now, if you didn't realize that, if you did go ahead and put 7 pi over 6 plus pi n, 11 pi over 6 plus pi n, I'm not going to count it wrong. Okay. I'm going to hope that you would see that, but you don't have to. Is everybody okay with that? All right, good. Did anybody go home last night and get those? A few folks? Okay. All right. Well, as I said, up to this point, it's been pretty straightforward. We've just isolated the trig function. But what if the equation is a little more complicated? 2 sine of x cosine x minus sine of x equals 0. So you can use different algebraic techniques. You could use identities that we've seen up to this point. Okay. There is one method that I like that makes things a lot easier. What could I possibly be referring to on this problem? That's true. You could use an identity, but let's say we go ahead and do that. He recognizes this as a double angle identity, right? So I've got sine of 2x. Okay, is that a plus or a minus? That's a minus. Sine of x is equal to 0. Now we have everything in terms of sine. Could I go ahead and combine those? Why not? There you go. One sine of 2x, the other sine of x. So even though I have the same trig function, it doesn't help me out. And I'm still kind of stuck. So just look more basic. This one I wouldn't recommend an identity. Is there just something that you notice? What kind of expression is it? Is it a monomial, a binomial, or a trinomial? It's a binomial. It's got two terms, right? What do you notice about those two terms? They both have sign. That's the word I was fishing for. You could factor something out. So what if I factored out a sine? What would that leave me? So that'd be 2 cosine of x minus 1 is equal to 0, right? So this is one of those instances where I would not be able to isolate one of the trig functions, and I can't go ahead and rewrite all the trig functions so they're the same. I mean, we just saw that. So now we're going to use a property that you probably haven't heard of in quite a while. Starts with a z. You saw them a lot when you were factoring quadratics and looking for the roots. The zero what? Okay, the zero product property. Okay. What the zero product property says, if I've got two terms that are multiplied together and I get 0, then one or the other has to be 0. So if I'm multiplying these two, then that means either sine of x equals 0 or 2 cosine of x minus 1 equals 0. Okay. So you see how I can separate them, set them each equal to 0, and now I can solve? Anybody remember that one? Okay. You probably saw it first time when you were dealing with quadratics, when you had the two group factors. Okay. Now, sine of x equals 0, we can go ahead and solve that one, and then 2 cosine of x minus 1. Well, that would just be cosine of x equals what? 1/2. Okay. Does that look familiar? Cosine of x equals 1/2? Yeah, I mean, if we wanted to go ahead and solve it, where is cosine positive? Well, quadrants 1 and 4. So I would create two triangles in those using that ratio. But, if we already went ahead and solved it, there's no reason to do it again. That was one of our original problems in the notes. So pi over 3 and 5 pi over 3. Okay. So x equals pi over 3, 5 pi over 3. So that takes care of that one. Now, those will be solutions to the original. Okay. But what about sine of x equals 0? What quadrant would I put the triangles in? There we go. Because see, here's the thing. If I did go ahead and look at that as a ratio, it's always opposite over hypotenuse, right, for sine? Well, that means your triangle, one side would have length what? 0. So Christian's absolutely right. It's a quadrantal. So just think about the unit circle. Okay. You've got 4 possibilities. 0, pi over 2, pi, and then 3 pi over 2. So if you're not able to draw a triangle, it has to be a quadrantal. So remember, what variable does sine represent? it's always the y, right? So out of these 4 locations, which ones have a y value of 0? 0 and pi. There you go. So at 0, you have the coordinate 1, 0. At pi, you have the coordinate negative 1, 0. There you go. Any questions? Okay. Now, I would probably solve number 8 similar to what we just did in number 7. It says cotangent of theta times cosine squared of theta equals 2 cotangent of theta. Okay. So what would you guys recommend I do?
You can divide a cotangent and it'll be cosine squared equals just like 1 cotangent.
So you want to divide through by cotangent? No, that would be eliminating that particular one. What if solutions made that true? Okay. What if I did this? Remember I said we could do it very similar to number 7? Okay. So I've got cotangent of theta times cosine squared of theta minus 2 cotangent of theta equals 0 because those cancel. Now, Jack is absolutely right. We will be able to use the zero product property again after I do what? After I factor out cotangent. Okay? Because now I have a binomial with a common term. So if I pull out the cotangent, okay, what's that going to leave me? Okay, so cosine squared, because cotangent times cosine squared would be cotangent cosine squared, minus what? Just one cotangent? Well, if I put a cotangent here, then that would give me cotangent squared, right?
Oh, okay.
So I just want the minus 2, right?
Oh, wait, okay, I see.
Okay.
Sorry. Yeah.
So again, I was able to separate them into a product using factoring, and I can go ahead and use the zero product property. So each term, remember this binomial is still considered to be one term, I'm going to set equal to 0, and I can go ahead and solve. So cotangent of theta equals 0, or cosine squared of theta minus 2 will equal 0. Okay. Now remember, even though we've come across now an equation that has cotangent, okay, if necessary, I can still draw the triangle, and it comes down to his ratio, because that's what's going to give you the special right triangle. But what do you notice about cotangent of theta equals 0? It's another quadrantal. You can't create a triangle with a side length of 0. So you're going to want to look at his ratio, x over y. Okay. Now, help me out with this one. What would cosine of theta equal? Plus or minus the square root of 2. Because I have to add the 2 over, and then I would take the square root, right? Okay, so try to solve those. You should only be able to get 2 answers. Okay, you should only be able to get 2 answers. And while you're doing that, I'm going to go ahead and draw another unit circle. Okay, now you may still be working on the cosine portion of it, but hopefully you've already gotten the cotangent done. Since we know it's a quadrantal, there's only 4 locations we can look at. Okay. So which of these 4 locations in the ordered pair can I take the x value, divide by the y value, and get 0? Where's that going to happen?
Pi over 2.
It'll happen at pi over 2, because, see, we have the ordered pair 0, 1. 0 divided by 1 is 0. Okay, so theta is equal to pi over 2. And what's the other location? 3 pi over 2. Because this ordered pair is 0, negative 1. See, I can't do 0 or pi because 1 divided by 0, for example, that's undefined. So those guys are out. Okay. Now remember I said there's only how many answers? There's only 2. Okay. So let's see why we're not going to be able to solve cosine of theta. Okay, so let's see, there's a couple of reasons why, and it really depends on what you see first. But let's say you run through the normal process, cosine theta equals plus or minus square root of 2. Okay, how many triangles would I draw? I would draw 4, because where's cosine positive and negative? It's in all 4 quadrants, right? Well, let's focus on just one. Let's focus on quadrant 1. So let's say we were going to draw the triangle without noticing what's happening. Well, the ratio is the square root of 2 over 1, right? What's cosine's ratio? It's always x over r. So this base would be the square root of 2. That would be 1. Does anybody already see the problem? It's not going to be special because what do you notice about the hypotenuse on the leg?
The radius.
Okay. In a right triangle, can a leg be longer than the hypotenuse? No. The square root of 2 is 1.41. Okay. In fact, if you were to use the Pythagorean theorem, you're going to get an imaginary number here because of that. So you can't create a triangle. So that's already telling me there's a problem. We shouldn't be able to get a solution out of this. But let's say you go ahead and look at it another way. Okay. Now you'll notice we are working backwards from the ratio to find the angle measure. So when we were doing that before, we used the inverses, right? We're not using the inverses to help me solve this, but those rules still apply. So let's say I went cosine inverse of the square root of 2 is equal to theta. We're taking the ratio and we're going to plug it in the inverse cosine to help me find the angle, right? Does anybody remember what's the restriction interval for whatever ratio you put into cosine inverse? It's been a while since we talked about it. Not 0 to 1. You're half right. Negative 1 to 1. Well, square root of 2 does not belong to that interval. So again, I'm going to have a problem. So see, there's different ways that you could see there's not going to be a value of theta that will give you a square root of 2. And really that makes sense because on the unit circle, what's the radius? 1. The furthest out you can go is 1. Is everybody okay with that? So it is possible that sometimes maybe some equations will not have an angle measure that'll make it true. Okay. Now, we got one more. This one, I'm going to help you get down to the point where we can create the triangles, and I'll let you take it from there. But it says 2 sine squared of x equals 2 plus cosine of x. Now, if I have an equation like this, and I'm not sure what to do, the first thing I do, right, Enzo? Right. I go ahead and move everything to one side and see if anything happens. Okay? So let me go ahead and pull the 2 and the cosine x over. So 2 sine squared of x minus cosine of x minus 2 is equal to 0. Okay. Now, it kind of looks like a certain type of equation. What am I referring to? Think about the trig function just being a variable. Looks almost like a quadratic, right? Now, we can actually solve these as quadratics, but the problem is I've got sine and cosine. two different trig functions like that, there's not a whole lot I can do the way it is. So we can't factor it, okay, because of the two different trig functions. There's no way to isolate one without having the other trig function on the other side. So this is a problem where I would think maybe an identity could help me out. Maybe I could use an identity to make one trig function look like the other. Where could I possibly be going with this? Is it possible to change a sine to a cosine or a cosine to a sine? How? Okay. We have an identity that says sine squared of x plus cosine squared of x is equal to 1, right? And luckily I have a sine squared right there. So what would sine squared equal if I did that?
1 minus
There you go. So 2. So in place of sine squared, I'm going to use part of the identity. 1 minus cosine squared of x minus cosine of x minus 2 equals 0. So this actually helps me out more than you know. Instead of having all these different trig functions, now I've got one equation that all uses cosine. So that's going to make it a lot easier to deal with. Okay. So somebody distribute that 2 for me. What would I get?
2
Okay. So that would be 2 minus
2 cosine squared.
2 cosine squared of x minus cosine of x minus 2 equals 0. Okay. And that's why I keep saying I think this is going to be the most difficult part. Can I simply just isolate the trig function? Do I have to use some kind of algebra technique like factoring? Will an identity help me? And the more of these you do, the more comfortable you're going to become with them. But it might be difficult in the beginning to figure out what's the best method. Well, what happens here? Yeah, the 2's cancels. 2 minus 2. So I've got negative 2 cosine squared of x minus cosine of x is equal to 0. Now, had the 2's not canceled, had I had a constant, we would have actually ended up with a trinomial quadratic. And I'm going to show you what to do with those tomorrow. But with what we've seen today in previous problems, where would you go from here? I can't combine the cosines because one's squared and one's not, but I can do what? Christian's absolutely right. We can pull out a cosine. If I can't combine them, maybe I can factor one out. Now, there's a little forgotten rule about factoring, and in the long run, it really doesn't make a difference, but if you're ever going to pull out a GCF, if the first term is negative, you want to pull the negative out with it. So bless you. So I'm going to say negative cosine of x times what? Would give me a negative 2 cosine squared.
Cosine.
So 2 cosine x. Because the negative times the positive will give me that negative, right? Now, because we pulled out the negative, what happens to this one?
Plus.
Plus what?
1.
1 equals 0. So I wasn't able to combine them, but I am able to use what? What's that property?
0.
The 0 product property. So the terms in this group, I can go ahead and each set them equal to 0. So negative cosine of x equals 0, or 2 cosine of x plus 1 is equal to 0. Now this one right here, negative cosine of x equals 0, isn't that the same as just cosine of x equals 0? Yeah, you can just multiply through by a negative or divide through. Okay, completely up to your choice. Okay. In fact, you'll notice that one's a what? Quadrantal. I would not be able to create a triangle with that. Okay. This one here, cosine of x. If I subtracted the 1 divided by 2, negative 1/2. Okay. That's going to be the tough part in some of these cases, just getting to that point. So this is what I would like you to do for tomorrow. Take these two little equations, find me the solutions on the interval from 0 to 2 pi. So that's where we'll start tomorrow. We'll check those answers, and then I believe we are on the last page of the notes. Okay? All right, good. Good, good, good. Whoop, that's not it. Okay, let's go ahead and get those calculators up to the front, please. Okay.